All right, today we're going to talk about pressure and gas laws, which should be really pretty straightforward um, because it really is just the same as it was last year. So, all right, first if we talk about gases for a little bit, gases we know have no distinct shape or volume. They'll fill any container. And this is all related to the kinetic molecular theory, which we will cover, but those main ideas. Because they don't have a lot of attractive forces and they're really far apart, they're very easily compressed. They also will mix completely with any other gas, and this is called, oops, it's not going to let me write. This is called diffusion, okay, the spontaneous mixing. And again, we'll come back to that a little bit later as well. The other thing it does is it exerts pressure on its surroundings. And if you just think about it, we know gas particles are in constant rapid random motion. And if we have them contained in something, as they're rapidly moving, they're going to collide. They're going to collide with each other, and they're also going to collide with container walls. And those collisions with container walls are what are going to give them the pressure, excuse me, on its surroundings and on its container. Now, historically for measuring pressure, we measure the barometer. And when you see like on the weather, you know, a high pressure system, low pressure system, this is the historical thing. And you fill it with mercury because mercury is a liquid at room temperature. It's one of the only elements. And essentially as mercury will flow out of the dish and out of the inverted tube until it's equal to the atmospheric pressure. And remember here, this downward arrow is the atmospheric pressure pushing on the mercury. So the higher the atmospheric pressure here, the more the mercury is going to rise in the tube. Obviously it will be lower the less those arrows. So that's just excuse me, kind of common practice for barometer. Again, atmospheric pressure, is results from the mass of the air being pulled toward the earth by gravity. Varies with altitude and weather conditions, but we're going to refer to atmospheric pressure a lot in this unit. A manometer, I'm not going to ask you about a manometer. I'm going to tell you about it anyway, just in case you have to hear it, but it measures the pressure of a gas in a container, so that's what's different. Gas has less pressure than the atmosphere, so the mercury is closer to the chamber. Excuse me. The gas will have more pressure than the atmosphere if the mercury is further from the chamber. So this is the setup. I'm not going to ask you about it just so that you can see, but it's measuring the gas, which again, here is a gas pressure greater than atmospheric pressure, so it's pushing the gas away, less than atmospheric pressure, so it's letting the mercury come closer. All right, then we have units of pressure. And for units of pressure, you've got millimeters of mercury. It's the most common since mercury is used in manometers and barometers. You also have torr. Those numbers are equal to each other. Standard atmospheric pressure, which is ATMs. Then you also have pascals. Okay, it's due to the guy from Pascal's triangle. It's an SI unit. It's newtons over meter square, which is still kind of a measure of force and pressure. And here are all the unit conversions. Now, I don't have it in front of me. I think some of them are on the AP Chem sheet, but I'm not totally sure which ones are on there. But these are all our conversions. And for an example, you know, pressure, we've got 49 torr. Put it in atmospheres, pascals, and millimeters of mercury. There you go. You've got your answers right there. Okay, pretty straightforward. Canceling out units, 2 sig figs, and all our answers, and we're good to go. All right, let's talk about gas laws. On the front of your packet, you have this nice, lovely little chart that kind of puts it all on one page, which I think is really nice. It's always easier to look at one spot, but here come the major gas laws. First one is Robert Boyle. He really got into studying gases just by going to a multi-level home and looking at its effects on volume in a closed gas. And the J-shaped tube was just a way to keep that. And essentially what he found is that the pressure and the volume are inversely proportional. And so it holds precisely at very low pressures. Okay, so you have to kind of keep things a little bit low on that. And then his equation is P1V1 equals P2V2. So let's do an example here. And the gas laws almost always show up on the AP test, but They're the gimme points. So you just, if it seems that simple, plug and chug and go for it. Okay, you have a 1.53 liter sample of gaseous sulfur dioxide at 5.6 times 10 to the third pascals. If the pressure is changed to 1.5 times 10 to the fourth pascals, what will be the new volume? Now, this is in liters. It doesn't have to be in liters. It could be in milliliters or centimeters cubed, but it just has to be the same. Okay, and same goes for your pressure units. This is one of the curveballs. They may give you pascals and they may give you atmospheres, and you've got to convert one to the other first. But here's your equation. P1V1 equals P2V2. Plug and chug, you end up with 0.57 liters because those pressure units cancel out. 2 sig figs for our answers. All right, Charles's law was discovered by a French guy. He was the first person to fill a balloon with hydrogen gas and make a solo balloon flight. Because of density and those different things, and he found that volume and temperature are directly proportional. And here is our equation there. And for any gas at negative 273.2 degrees Celsius, the volume is 0. That is what we refer to as absolute zero or 0 Kelvin. And it's never actually been reached here on Earth because there's always some heat flow. We've gotten within, I think, a few tenths of a degree. See, there you go. But we haven't quite gotten there because there's always a heat source. Kelvin system has no negative values. And although this has the 0.2 on it, which most of us probably remember, add 273. Don't worry about the 0.15 there. Okay, I forgot to delete it. Your notes doesn't have it written that way, but it's just at plus or minus 273. Okay, so here we've got a sample of gas at 15 degrees Celsius and 1 atm has a volume of 2.58 liters. What volume will the gas occupy at 38 degrees Celsius and 1 atm? Now, since the pressures are the same, you don't have to include them. You don't necessarily have to convert these to degrees Celsius, but well, no, I'm lying. You do need to always convert it to Kelvin. You always want to go from Celsius to Kelvin so that you don't end up with negative numbers. And that's really what they're trying to prevent against. So it's just good practice. And since our volume was given in liters, we also have 2.79 liters after we plug and chug, because the kelvins cancel out. Okay, Avogadro's law, which we didn't focus a ton last year, but he said that equal volumes of gases at the same temperature and pressure contain the same number of particles. So it still is related to numbers of particles. That's why we've got Avogadro's number. And this is just that volume and N are directly proportional. If you think about it, it just means that if there's more atoms, it's going to take up a larger space. So it's not really a huge reach, but this is also his equation as well, which I show you because it does occasionally show up, but for those good at math people, you'll see the same relationships are present from the ideal gas law. Okay, so let's say we have a 12.2 liter sample of gas containing 0.50 moles, pressure of 1 atm, temperature of 25 degrees Celsius. If all of this oxygen was converted to ozone, the same temperature and pressure. Okay, so that means we do not have to look at temperature. We do not have to look at pressure. We can simply look at moles, and this is using our balanced chemical equation as well in order as a reactant. So once we figure out how many moles of ozone that we have, okay, it's just a mole to mole conversion, and if you wanted to, you could have moles change in X and do it that way. That would get you there too. Remember, this is going to be another one when we get to gases that if we use the stoichiometry chart, we're going to have to kind of leave off the first two, and I'll show you some of the other conversions that we have for those. Then we can use Avogadro's law, plug and chug, and figure out that it's going to take up 8.1 liters. Okay, since ozone is going to have fewer molecules, it's going to have a smaller volume, and so there's that direct correspondence. Okay, Gay-Lussac's law looks at pressure and temperature. And remember we made our PTV cards last year to kind of help us remember these things, where we put little holes and if one went up, the other went up and vice versa. So we'll probably take a look at those again as well. But for pressure and temperature, to plug and chug here, you've got gas in an aerosol can at 3.00 atms, 25 degrees Celsius. The directions on the can, which is true, warn the user not to keep the can in a place where temperature exceeds 52 degrees Celsius. What would the gas pressure be in the can? Here's our plug and chug. It would be 3.27 ATMs, and essentially that's the short version of that is that you get to the place where the container cannot withstand that pressure, and so it's going to go kaboom. Okay, so there's gas laws and pressure. Hopefully not too stressful, and I hope